Hi, I've been asked several times by different students to do a little bit more on the resting membrane potential and how potassium levels in the blood affect that. So I'm going to go through and review the resting membrane potential that you learned about in Biology 160. Hopefully it was reinforced in A&P 1. And it's useful to understand how hypo and hyperkalemia affect cell membranes. And it's important because the heart is critically affected by high or low potassium levels. Arrhythmias will form. So I'm going to start out reviewing the resting membrane potential. And we'll then take a look at hypo and hyperkalemia and how that affects the resting membrane potential. And what's key to this whole story is the potassium diffusion gradient. That's what you really want to focus on as we go through the review of the RMP, the membrane resting potential. So let's review that first. So let's make this the cell membrane. And just to get oriented, this is the extracellular fluid, so that's the outside of the cell. And this would be the intracellular fluid, cytosol, cytoplasm. And this is our sodium-potassium pump. So let's put the pump in. I'll just represent that, something like this. And we'll label it the sodium-potassium pump, sometimes referred to as the sodium-potassium ATPase, because it hydrolyzes ATP. So you remember that it is pumping sodium out of the cell, 3 sodium ions each time the pump cycles, and 2 potassium ions are coming into the cell. And that creates a chemical gradient. And we wind up with a much higher concentration of potassium inside the cell. So I'll represent a relatively high concentration with an up arrow. In standard chemistry nomenclature, if you put something in square brackets, that just means concentration of. So that would read concentration of potassium. It's relatively high. And then on the outside of the cell, it would be the opposite. There's very little potassium outside the cell. And that's what we're going to be talking about with hypo and hyperkalemia, is this potassium level, not what's inside the cell. So to get back to this pump, you know that it hydrolyzes ATP. Lots of different ways you can denote that. I'm just going to write ATP on the pump. And you need to remember that it hydrolyzes ATP. Okay, for the sodium, it's pumping sodium out of the cell, so there is a relatively low concentration of sodium inside the cell, and a relatively high concentration of sodium outside the cell. You've seen that numerous times with the kidney and filtration. Okay, so what that does is that it creates this chemical gradient. Chemical, let's say, ion gradient. Just meaning that there's more of one ion inside the cell or outside the cell. So you have to remember that potassium is high inside the cell and quite low outside. And that sets up a charge difference across the membrane. And if you just look at the number of positively charged ions that are going outside the cell, there are 3 sodiums that are going outside, 2 positively charged potassiums going inside. So if you looked at nothing other than the number of cations being pumped across the membrane, it would give you a difference. And there are more positively charged ions being pumped out, 3 sodium, than positively charged ions coming in, the 2 potassium. So that sets up this electrical gradient that you're familiar with. So this is sometimes referred to the 2 together, the electrical and the chemical, as the electrochemical gradient. Sounds fancy and complicated, but it's not. Electrochemical gradient just means that there are differences across the membrane. Okay, that accounts for some of this resting membrane potential. Most of that resting membrane potential, though, the difference is going to come from potassium leakage. So I'm going to put in another major piece of this story, which are the potassium leakage channels. And we'll label this a potassium leakage channel. So potassium is constantly leaking from where it's higher, where there's a higher concentration, where there's a lower. So the potassium is constantly leaving the cell. And by the way, this transport process is facilitated diffusion. And as those potassium ions leave the cell, left behind are negatively charged ions, anions. Anions left behind. And anions are negatively charged ions. So, as you have more of the negatively charged ions left behind, that's what gives you most of this negative charge at the membrane. Now also remember that this resting membrane potential that we're drawing here, positive on the outside, negative on the inside, occurs only at the membrane. It doesn't mean that the middle of the cell is negatively charged. This whole story is right at the thin, oily film of the cell membrane only. So if we're going to represent this RMP now, this membrane potential, we might draw a set of axes, and maybe we'll put this at minus 70, and maybe this is at 0, and our scale is millivolts, and time. And by the way, you should know how many millivolts there are in 1 volt. How many of anything there are that has millions of prefix. So this would be our resting membrane potential, our RMP. And remember also, in these stories of excitable membranes, there's going to be some sort of threshold. These are excitable membranes. We're talking about heart cells, muscle cells, nerve cells. It's all the same idea. And what has to happen is that the cell is at rest. So this story above is going on. The pump is running all the time. Potassium is leaking out all the time, comes to equilibrium, and it means that the inside of the cell is about minus 70 millivolts relative to the outside. And for the cell to become active, it has to depolarize up to threshold. And you remember that from earlier. And once that membrane depolarizes to threshold, here it's going up, it's less negative, it's less polarized. Once it hits threshold, then we have an action potential that is formed. I'm not going to go into the action potentials, we've already done that. This lecture is about the membrane potential, it's minus 70, and about how potassium levels affect it. And it's going to be, again, the potassium level in the extracellular fluid. So that's the basic story there of how the resting membrane potential is formed and how it's maintained. It's constantly requiring ATP hydrolysis. At rest, when you're sleeping, about 25% of all the ATP that's being hydrolyzed in your body is being used just to drive those sodium-potassium pumps. So it's a significant activity. So let's now look at hypo and hyperkalemia. And to sort of review, that is going to be dealing with this part of the story. That's what's going to be, that part of the story is what's going to be affecting this part of the story. So let's go to the next slide and we'll do this again. So let's start with hypokalemia. It doesn't really matter. Hypokalemia, and what you want to be able to explain and to think about is that how hypokalemia leads to hyperpolarization of the RMP. So let's draw another cell membrane. Something like that, it's good enough. Again, get ourselves oriented, extracellular side, intracellular side. And I'll throw in a sodium-potassium pump just so that we remember it's still there, pumping ions mindlessly all the time that you're alive. And it's requiring ATP hydrolysis, however you want to represent that. There's lots of different ways. But it splits that terminal phosphate. Energy is released to do the pumping. And if you want to just review again, it's high sodium outside and low potassium outside. And just the reverse inside. Low sodium, high potassium. You don't have to draw this if you remember it clearly. Okay, and then let's put in our charge. And let's put in our potassium leakage channel, because that's the critical part of this story. And potassium is leaking out. And remember what that is normally doing to the RMP. It's making the membrane more negative. The more leakage, the more negative. I'm assuming that the camera is capturing everything past that line. Okay, so now you're remembering that the story is dependent upon the potassium diffusion gradient. And again, that's this part. Okay? So we now have hypokalemia. So with hypokalemia, we have even less potassium now. So I'll draw two down arrows. So where our potassium levels are not in the homeostatic range, we have too little potassium. So the idea is, what does that do to the diffusion gradient? You can think of the gradient in terms of a hill. The steeper the hill, the faster the ball rolls down the hill. And the less steep the gradient, the less steep the hill, the slower the ball rolls down the hill. So we're not talking about balls rolling down a hill, we're talking about potassium leaking out of a cell. So with lower potassium, we have a steeper diffusion gradient. Steeper potassium diffusion gradient. The idea is that more potassium leaves. There's less potassium blocking its exit, if you will. So more potassium leaves. More potassium leaves. Don't confuse this up arrow that I just drew in green with the two red arrows indicating hypokalemia. So how does that affect the RMP? So here was our RMP. Here's minus 70 again. 0 millivolts time. And we're sitting here. And let's remember that we have a threshold level in here somewhere. Maybe it's minus 50, whatever. And we have hypokalemia. So as more potassium leaves, that makes the cell more negative inside, and the cell membrane hyperpolarizes. Maybe we go down to a new RMP. So this was due to hypokalemia. And if this is where we were originally, and now we're at this point, it's pretty clear that it's going to take a larger stimulus to reach threshold than it did before. This was normal, and this is with hyperkalemia. So, is the cell going to be more excitable or less excitable with hypokalemia? It's going to be less excitable because it's going to be harder to reach threshold. So it will depolarize, it will generate action potentials more infrequently. It'll be inhibited, sedated, if you will. So that's hypokalemia, leading to hyperpolarization and inhibition of the membrane potential. So we'll do hyperkalemia, and it's just the opposite. And hyperkalemia is going to lead to partial depolarization. Of the RMP. We'll essentially be raising it on that graph. So let's whip out another quick drawing here. I don't know if it's necessary, but we will anyway. Extracellular fluid, intracellular fluid, the sodium-potassium pump with the 3 sodium out and the 2 potassium in. And we're hydrolyzing ATP. Same old, same old. Okay, and let's put in our potassium diffusion gradient, or potassium diffusion channel. Potassium leakage. And you know that we have a high concentration of potassium inside the cell and a low concentration of potassium outside the cell, and the potassium leaks out. Now, sometimes students get kind of confused. When we're talking about hyperkalemia, we're talking about a tiny amount. The difference between the inside of the cell and the outside of the cell never changes. There's always much more potassium inside the cell than outside. So when we're talking about hyperkalemia, we're meaning just a small difference. It's still much less than what's inside the cell. If those ever flip-flopped, the cell wouldn't work. And if it's a heart cell, the heart won't work. So when we're talking about hyperkalemia, just remember that this is always still lower than what's in the cell. But we now have more potassium ions outside the cell. So we'll just draw a few extra potassium ions outside the cell. Doesn't take much of an increase to have dramatic effects. Extra potassium ions outside cell. That's our hyperkalemia. Okay, so as more of these potassium ions are crowded on the outside, do you think that's going to cause fewer potassiums to leave? Yeah, you know that like charges repel each other, so we have more positively charged ions out there. There's more back pressure, if you will. There's less of a gradient, so we wind up having fewer potassium ions leaking out. Fewer. And you know that they're positively charged. Therefore, the intracellular fluid becomes more positive. Less negative. So if we draw the picture, minus 70 again, 0 millivolts, and here is our starting RMP, and we'll draw our threshold in again. And now we have hyperkalemia. Remember that the sodium-potassium pump is always running, so it continues to pump in potassium, and there's fewer leaking out, so let's say less leakage. So I didn't put my charges on the membrane to begin with. You remember what those are anyway. Let's stick with black. That's our minus 70 difference starting. But now we have hyperkalemia. And we have more positive charges inside the cell. It's less negative, so the membrane starts to depolarize a little bit. And maybe it stabilizes at this point. So this is our new RMP. It's closer to threshold. So this event is hyperkalemia, which caused that depolarization. Okay, so the result of this is the cell more or less excitable. In the previous slide, we saw that hypokalemia made it less excitable. In this case, their membrane now is much closer to threshold. It could be just a little bit closer to threshold. And it takes less of a stimulus to hit threshold than it did before. We're already halfway to threshold. So initially, the cells are more excitable. With hyperkalemia. More excitable, let's say, closer to threshold. However, there's a problem in that it eventually makes it harder for the cell to repolarize back down to the -70 level where those voltage gated ion channels reset. So at least initially it's more excitable. Initially. And then later, it's more difficult to repolarize. And it depends on the size of this potassium level change, whether it's a small amount or a large amount. So later, more difficult for cell to repolarize. And if this is a heart cell, that's not a good thing, because the heart cells have to repolarize before they can depolarize and contract again. So it leads to arrhythmias of the heart. And when a veterinarian euthanizes an animal, a dog, cat, horse, or anything else, they will euthanize the animal by giving them an injection of potassium, usually potassium chloride. It's just like table salt, but instead of sodium chloride, it's potassium chloride. And that dose of high potassium shuts down the heart. The heart can't repolarize, it stops, and the animal dies. So it's important to appreciate hypo and hyperkalemia. It doesn't take much of a difference in that extracellular concentration to have a dramatic impact on the membrane. So I hope that helps. And ask questions if you have them. Bye.